We try to discuss the combination of output characteristics and transfer characteristics. Here the x-axis is same radius, which is going to be in volts. Y-axis is drain current, which is in milliamperes. You can make scalars in terms of 5 volts, 5, 10, 15, up to 25 volts. Y-axis you can make the scale with current as in milliampere. 1 milliampere, 2 milliampere, 3, and plot up to 6 milliamperes. And here the output characteristics you must show for some positive values, some negative values. Don't show more negative values. So start with negative value, which is close to the x-axis. This is for VGS as minus 4 volts. You have to show some positive values and as well as some negative values. This is VGS is equal to minus 3 volts. This VGS is equal to minus 2 volts. Minus 1, and so for VGS is equal to 0, and also show 1 or 2 positive values. This is VGS is equal to plus 1 volt, VGS is equal to plus 2 volts. Almost you can see beyond the pinch out, you can get straight line. So just draw the straight line. So this is VGS is equal to plus 2 volts. Also make a note in this characteristics. We have considered some values of negative. This corresponds to depletion mode. Even though the device is depletion MOSFET, you can operate in both depletion mode as well as enhancement. This is called as enhancement mode. The reason why it is called enhancement is because current will start improving. You can see the current is increasing. But as you go depletion more and more negative, current start decreasing. For example, for VGS is equal to say minus 6, current will be 0. Curve based on x-axis. So having drawn this, one can draw the transfer curve adjacent to this. Okay. Just what to do is draw the x-axis same as this, and you can show here for more values we have here the negative. So this is my ID curve for ID axis for transfer characteristics. Here we have minus VGS, which is in volts along negative x-axis, plus VGS, which is going to be in volts for the positive x-axis. This is origin. You can go in terms of 1 volts, which is plus 1, plus 2. You can see the curves here. We don't have more than plus 2 here. Just I can stop it at plus 2. Once we go run. Say for example, this is plus 3, VGS is equal to plus 3, VGS is equal to plus 2, plus 1, and 0. And for negative VGS, you can show down the second quadrant. You can see that this is minus 1, VGS as minus 2, VGS is equal to minus 3, VGS as minus 4. You can see we have not taken VGS less than minus 4, we stop at minus 4. Here also we can stop it at minus 4. Okay. That means our curve will be up to this point, not beyond. Now what we can do is just wherever there is a pinch off, and locate the pinch off, the time being here, pinch off where the current becomes constant. You can say pinch off will be very close for this VGS is equal to minus 4. Pinch off will be here. Pinch off. This is nothing but pinch off points. Okay. These points you can join together, that becomes a locus of the pinch off point. You get almost like a linear. And here is nothing but locus of pinch off. And beyond this, current becomes almost a constant. So wherever the pinch off has been reached, from there you can draw the horizontal straight lines. See here approximately. Okay. This you can find the intersection point here for minus 4. Similarly, you can draw the intersection point for minus 2, minus 3. This for minus 2. For minus 1. Next we have for 0. For 0 we have at this point intersection point. For plus 1 intersection point at plus 1. Last we have plus 2. Just connect all these curves to get a transfer. Okay. You join all these lines that results in a transfer. Make it almost as straight. The region which you see on the right hand side of the left hand side of the transfer is called depletion region, and the region which you see towards right hand side of the transfer curve is called enhancement region. You can give a title for this figure, which is, let us say this is figure A. This is transfer characteristics. This is going to be the output characteristics. And then combining together, we can say this is D MOSFET, depletion MOSFET characteristics. So go through this. For your reference, I will draw the device again. So this is an N-channel depletion MOSFET. P-type substrate, when two N plus regions. There is a channel which is connecting these two N plus region. When metallic contact to make electrical connection. And the gate region also is covering with metal. We have a substrate region which also has metal. We indicate the silicon dioxide by shading with horizontal lines. This is source, gate, and plastic element. We have shown circuit symbol for this device. Okay? N channel as well as P channel depletion MOSFETs. So we draw the circuit connection, and we will consider the three cases to explain the operation of this. But this the symbol of N-channel depletion MOSFET. Here we consider the three different cases. First case, let us consider with VGS as 0. Between these two things, they have between a drain as well as a source. Voltage is VGS. This is the gate terminal and the source. The voltage is VGS. And this power supply we connected here on the screen. Look at it. Why I have drawn these two things is using this circuit symbol is very difficult to understand the operation. Having this, it's very easy to understand the operation. You will see that literally what will happen with respect to the circuit voltage. I have classified this into three cases. One is case 1 with VGS as 0. Case 2, to explain the operation, I am going to consider VGS as some negative voltage. Lastly, we have a third case where we are going to consider VGS as some positive. That means the operation of the N-channel depletion MOSFET can be categorized into three different cases: VGS as 0, VGS as negative, VGS as positive. And circuit connection is essential. Of course, don't forget to ground it. So for the first case, okay, for case 1 is here. Circuit diagram for case 1 is here, where you can see that VGS remains here. But in all these three cases, we assume that there is some VGS. You can see there is a VGS exists because of that one connected to the power supply. VDD stands for drain power supply, which is similar to the VCC in case of BJT. Look at here, there is some drain to source voltage exists. As long as you apply here, there will be some voltage exists. You will apply VDD. But look at about VGS. VGS is important for us. You can look at here. Even here also we have three cases. Look at here, VGS 0, VGS positive, VGS negative. Three cases are there. I just want to show this. What happens when VGS is equal to 0? Circuit is here. When you want to make VGS as 0, rig of circuit is this way. And the short circuit gate and source. That means whatever the voltage we have here, same voltage also exists here at the gate. There is no voltage applied between the gate and source. But look at now device, whether device conducts or not, check out here. Because here it is very difficult to say whether device conducts or not. Look at this. Okay, I will do same connection here also. I will short circuit source and substrate, which is done here. Source and substrate are short circuit. I am not giving it substrate. Source is short circuit. Next, what else? You want to short circuit gate and as well as source. Let me short circuit gate and source. Short circuit. That means VGS is. Next, what else? We need to apply a power supply VDD across drain and source. I must connect a power supply with drain and source. Negative to the gate, not with respect to gate. I must apply with respect to source. Let me apply this. Negative. Okay. Is it clear? This power supply let me call as since it is applied between VDS, I can also call this as, instead of calling it as VDD, let me call as VDS. Because VDD is a thing, but it's a power supply. And this voltage creates drain source. This power supply creates drain source. You understand? For this particular circuit, device is shown. My question is now whether the current flows or not. Look at the current. There is a current. VGS is equal to 0. There is some current. This much amount of current is flowing. I will tell you the current. Current is flowing. Even though the VGS is 0. You know why this current is flowing through this device? Because there is a channel which is a N-type. Channel is there. Look at how electrons flow. Negative here. Electrons will start just like this. This is electron movement. Electron will flow like this. Electron movement. Let's see here. Through the metal contact, electron will be moving in this way. Okay. They will attract it to the positive terminal of the guide. This. Right? There is a path for the electron to flow. Negative N plus, they will repel each other. And they will start moving towards the drain region. You can see here also channel is a N-type. So through the channel, electrons will keep moving towards the positive terminal of guide. As you keep on increasing here VDS, what will happen? You keep on increasing this VDS across this. At some point of time, current will decrease. Instrument source primary income is 2.5 lakhs CSP. Required for 3 concession applications in 206 second floor. Who expected to have concession increases? Get those candidates to increase certain analysis certificates on before 11th of Mass cards of previous years were supposed to submit certificates if parents not like CET allotment letter, income or salary certificate previously. Xerox ID for Xerox ID for this. Okay, those are expecting concession. Okay. You understand this now? What happens if I apply a large value of VDS? You see that now? My VDS is 0. I am getting some amount of current here. As I keep on increasing your VDS, what is going to happen? At some point, current becomes saturated. We are supposed to see that when VDS is 0, up to here current is not increasing. This particular current is increasing for VDS is equal to 0. Okay. When VDS is equal to 10 volts, current starts increasing. But But beyond 10 volts, you can see for VDS, current has become almost constant. That means current is not increasing beyond. This particular region becomes more reverse biased. Okay, because you can see that N plus is straight to the positive of the battery and negative is straight to the VDS. In this particular region, it becomes more reverse biased. Due to that, current will be almost saturates. But the amount of saturation, you can see that when VGS is equal to 0, saturation happens say approximately 10. To draw the vertical line, it will reach at 10. Saturation happens at 10 for VGS is equal to 0. Look at for VGS is equal to plus 1, saturates little bit it increases. And VGS is equal to plus 2, saturation little bit increases. And the saturation is postponed when you increase the value of VGS. That means when you decrease the value of VGS, at lower stage itself saturation happens. Okay, you can see for VGS is equal to minus 4, saturation is happening here. For VGS value around 1 or 2 volts, saturation is happening. That's what we want to make clear for this. You understand case number 1? Case number 1 is VGS is made 0. When VGS is made 0, look at only this particular chart. I'll just make it in different colors so that you can visualize things and easily understand. So far what we explained is only with respect to this. Not with respect to any other. This is case number 1. Case number 1 gives you this particular. With respect to this curve, this characteristics, VGS is 0, you will get this particular point. See that? This complete curve here becomes 1 point here in the transfer. Because our this transfer curve is with respect to VGS and as well as I. When VGS is equal to 0, we take the first case. So this becomes a single. Okay. This complete curve here has been transferred. So here what you want to remember is when you make VGS as 0, if you keep on increasing the VDS, initially current will start increasing, but later on current becomes almost saturation. Current will not be increased beyond a certain value of VDS. Say for example 30% beyond if you go, VDS, the current will be calculated in the breakdown. That's the first case. What about second case when VGS is negative? Look at second case when VGS is made negative. I will change little bit in the circuit. I will apply here voltage. You can see negative, minus, plus signs. Okay. You don't have VG as 0 now. So this we call this power supply as VGG, negative power supply. Okay. Second case. You have to consider this case, second case. VGS is negative. But how do you make negative here? You connect a power supply in such a way that positive, negative. I am not changing VDS. VDS is kept as it is. But only thing is we change the VGS. VGS is not 0 now. It is negative. Now we can vary this voltage also and see that what happens when you go more negative. Okay. When you go more negative here, what type of charge particles are residing below this the channel region? You can see here. You are applying negative, you know the potential there, but look at here, you are supplying upper plate with negative type of charge particles, charges, and you see that below the silicon dioxide, what type of charge can this accumulate? Positive charge particles, right? Because where these positive charge particles are present, they are here. In the p type substrate, they are the majority charge carriers. Because of your separate gate with negative charges, this negative gate here attracts more number of charges into the channel region. All the positive charges will move like this in this fashion. The transfer positive charges accumulate here below silicon dioxide because they cannot cross the silicon dioxide. They will accumulate near the silicon dioxide. Now see if you apply VDS, will this cause any current flow? Because you can see there is a blockage here. The N plus is there, here we have N plus. But in between two N plus you can observe it, positive charges has been accumulated. Okay. Because of that positive charges, electrons cannot cross these positive charges. Electrons should have continuity. Now this continuity has been lost because of positive charges accumulated. If you increase more the VGS here, more number of positive charges you can see. That will completely block the 2 N plus regions. When those regions are blocked, obviously current flowing from source region to drain region will stop. That's why if you apply more negative, you see that what is happening. When VGS is minus 1 volt, you have some current, less negative. When VGS is equal to minus 2, you are going more negative. That means you are increasing your positive charges. VGS minus 3, current is gradually decreasing. VGS is equal to minus 4, almost decreasing. When you go beyond this, completely it blocks the current from source to drain. So you will not get any current. This particular region is called as depletion. Let's go to the case number 2. Case number 2, you will get all these characteristics. One is VGS is equal to minus 1, VGS is equal to minus 2, minus 3, and last we have. What about here? For the case number 2, all these points. See these points. So now nothing but negative values of VGS. What about last one? Last case? The VGS is positive. You can see for VGS is equal to positive, what will happen? This particular case, last case. How do you make the positive here? Just to change the polarity here. You can make it here this polarity as positive to the gate side, negative to the source side. This is VGS. Right? Look at here how you change similar change. You can make it here also, which is positive to the gate, negative to the source. And of course, the source voltage remains same. I am not going to vary that. Now see what will happen here. Positive drain voltage. That means the upper plate you are going to supply positive type of charges. You can see here upper plate gate is supplied with positive charges. What will happen below silicon dioxide? You will find negative charge particles. You will find more number of negative charge particles here, provided you apply more gate source. Where these negative charges has been come from? So they are the minority charge carriers also. So all minority charge carriers get attracted below the silicon dioxide because of the positive charge applied, positive charge applied to the gate. So all electrons will go like this. All electrons. Here this is minority. They will keep on moving to the silicon dioxide, below silicon dioxide. They will get accumulated here. And this accumulation of charge carriers increases the number of free electrons. These free electrons will make a continuity between these two n plus states and hence causes the current. Now if you increase your VDS, obviously current will flow because there is n plus region and there is n type here, electrons, and here again you have an n type here, so current will flow. Right? That's going to be the third case, and you get all these characteristics. You can see here this particular characteristics. Understood this? So different positive values of VGS, and here you get this particular points from starting from. This is for VGS. Understood this? So this is the behavior of the depletion type of MOSFETs. The only difference between depletion MOSFET and enhancement MOSFET is in enhancement MOSFET you will not find this charge. So that we will consider the next term. So if you have any questions you can ask before we go to the enhancement MOSFET. Any questions? So we'll draw the enhancement MOSFET. Starting in call this one as E-MOSFETs. Also this can be labeled as normally these MOSFETs are off. Normally off MOSFET. Why it is cut off? Because here for zero gate voltage in case of depletion there is a current flow. Whereas in this case, in enhancement MOSFET, when you make the gate source voltage as 0, you will not get any current. That's why this is called as normally off MOSFET. Whereas depletion MOSFET can be called as normally on MOSFET. Even for 0 gate source voltage, there is a current. And because of this, we can call depletion MOSFET as normally on MOSFET. Because at 0, there is a current. But about construction, I will show the construction of N-channel MOSFET. Again, here also we can have two types, N-channel as well as P-channel. We will have two N+ regions. And of course, for the N-channel MOSFET, substrate is of P-type. P-type substrate. This is a construction of N-channel MOSFET. For silicon dioxide, we will shade it with horizontal like this manner. Construction of N-channel enhancement MOSFET. This is a cross-sectional view of N-channel enhancement MOSFET. We can draw similar lines the construction of P-channel MOSFET. Just quickly draw the construction of P-channel MOSFET. P-channel MOSFET will have the N-type substrate. And we will find two P plus regions. You will not find channel here. You can see there is no channel if you have seen in depletion MOSFET. This is a construction of P-channel MOSFET. It shows circuit symbols in the single lines. can compare even circuit symbols which were drawn for depletion MOSFET. So this is circuit symbol for enhancement E MOSFET. This is an alternative symbol which I have done here by starting the source and substrate. If you look at these two symbols, both are the representation of N-channel E MOSFET. Similar lines, we can also draw the circuit symbol for P-channel E MOSFET, where arrow ones will be outward. SS indicates substrate region. And the last symbol you can see here, your short circuit again, source and substrate. So this is a circuit symbol for P-channel enhancement MOSFET. Just have a comparison of circuit symbols of P-channel and N-channel MOSFET with respect to depletion MOSFET. What you can observe here is there is a breakage here. As you see here, there is a gap here. This you don't find it in depletion MOSFET. In depletion MOSFET, you have continuity because channel was there, but over here channel has been broken. Right? You can see this region indicates here the drain region, source region, substrate region, and all are not connected. That's what this breakage shows. Right? And this arrow indicates movement of charge carriers. Okay. Same thing you can see here. Normally for the circuit construction, we will short circuit source and substrate. Do not apply any potential between these two terminals. Okay. So that's why under the equivalent circuit symbol is this. In our syllabus point of view, we can follow this circuit symbol instead of writing this circuit symbol. Anyway, we are not going to consider any voltage between these two terminals. We can consider always drawing this for circuits which are. And you can see another circuit symbol for the P channel, which is of opposite arrow mark is going outward. Again, there is a breakage. This is a drain region, source region, substrate region, and gate you can see here. And this empty space here, whatever it has been shown, it is a silicon dioxide. It's insulated, it will not connect. You can see that gate region and this drain, source, substrate are separated, right? That's what symbol is showing. That's why this is called as insulated gate MOSFET. MOSFET also can be called as insulated gate. Gate is separated from rest of the devices, rest of the terminals. So this symbol you don't find it in any other device. Now we had a comparison between these two devices, the N channel E MOSFET and P channel E MOSFET. So you see the replica here, P substrate, N substrate. Diffusion you can see N plus region, two N plus regions are here, and two P plus regions are here. And of course, there is a metal contact which is same as here. There is no change. Okay. Terminals also, source, gate, drain, and substrate is here. Okay. If you understand one of these operations, later on understanding the other device becomes easy. Now look at this one. Let me try to expand this. So look at this. What kind of voltage here? Before now going to the voltage, if I apply gate source as 0, what do you think device conducts? Just like we analyzed the previously the depletion MOSFET with the 0 gate source voltage, with negative gate source voltage, with the positive gate source voltage. Here I cannot take negative and 0. The reason is device will not conduct at all. So those two cases are eliminated. So here we start with 0 and positive voltages. So we is checking for 0 what will happen, and if it does not conduct, we will not use it. Okay. So let us look into the working of this MOSFET. Operation of MOSFET. Again you can see that I will apply gate source as 0. Short circuit gate and source. But I will apply some VDS. Let's say we are applying VDS. Negative, positive. So there is a VDS. This voltage can be called as VDS. The per substrate. Look at that simple. The short circuit the source and substrate. Let us short circuit this source and substrate. Short circuit source. The voltage between the source and substrate is this is grounded. So ground means it is a 0 volts. Same 0 volts is also here at the source. Now, since do you think if you apply increase your VDS, do you have any kind? Because there is no continuity between these two. Okay. In between, you can see through N plus region there is a P type substrate. Okay. So current will not go from source N plus region to drain N plus region. So device will remain off, but VGS has 0. That's why it is called normally off. What about the VGS is negative? In case if I assume that if I apply negative VGS,
there is no N channel, so there is
even you are increasing number of positive charges only here, right? If you apply here, say negative like this, positive here. If this is the case, what you are doing is that here, this region is important for us. Where we create a connectivity between these two N plus regions. Negative here, this plate becomes completely negatively charged, and below positive here, below silicon dioxide, what kind of charge carrier this will attract? A negatively charged plate obviously will attract positive charges below silicon dioxide. In case if you increase this more and more negative, so obviously this becomes more and more positive. These two regions remains isolated, so there is no connectivity. So device is not. This is no use. So 0 is also no use, negative also no use. The only possibilities are positive. Let's try with positive. So let's say positive to the gate terminal, negative to the source terminal. Now look at what we have. This is our VGS. I am not touching upon VDS. VDS is always some voltage I am applying. Say for example, this fixed 2 volts I am applying. We will not disturb VDS. Only our control is with VGS. This is a switch. How do you make this device on or off? The fan or any electrical appliances. Turn on, turn off. Turn on it, current will flow. Turn off it, current will flow. Same thing is possible here. That's what we are checking, right? Our gate, where is my switch now? This is my switch. If you want to turn off this, apply 0 negative. When you want to turn on this, apply positive. If you apply positive voltage here, whatever the current is flowing, I may have some application here. Current will be drain and source. Okay, if you want to feed current to your application, then definitely you must apply a positive source. So positive here will induce upper plate of the silicon dioxide becomes a positive charge, fully positively charged. Now this has enough capacity to attract electrons, which are minority characteristic in the substrate. So all the electrons will be present. Therefore, in case of depletion MOSFET, we created this channel There was built-in N-plus channel, N-type channel, but in case of enhancement, there is no channel. You have to create this path. How do you create this path? The applying path to give. This charge carrier itself will act like a path from the current flow from the source N-plus region to the next. More charge carriers will take here, road becomes more wider, path becomes wider. That means it can cause more number of charge carriers to cross this path. More than the You understand this? That is the basic principle of operation of n-channel. But also look at here. Suppose if you fix the VGS, say for example 2 volts. In case if you increase your VGS, what will happen? Say 3 volts, 4 volts, 5 volts, 6 volts. At some point, okay, since it is reverse bias, this region this side will get more and more reverse bias. Okay, pinch off will happen at this point. There is a diode here, right? You can see here there is N plus P diode, N plus P diode. There are 2 diodes are there. Question arises here, which of this is power biased? Obviously, this side is reverse bias. You can see N plus is tied to the positive of the battery, and the substrate is tied to the negative. P substrate negative, positive N plus. Obviously, it is reverse bias. That means if you go for larger VDS, what may happen is pinch off will happen. That's why you see constant current in the curves. Initially, you see that when it increases from 0 to say 1 volt to 2 volts, 0 to 1 volts, that will start increasing. But after 1 volts, what will happen is pinch off, current becomes sideways. Now, can you plot this as a characteristics if required? So far, whatever we explained here, draw this as a characteristics. Output characteristics, transfer characteristics. Just a 1 minute job. As usual, radius is volts and area is going to be milliampere. Let's take it the scale as 5, 10, 15, 20 and 25. Here to start with VGS as don't go for negative. As we have been known for negative 1, 0 will not connect. Start with at least 2 volts. Start with this is going to be for VGS as plus 2 volts and go towards more positive. 3, this is 4, 5, we can go up to 6. This is VGS as 3 volts, VGS as 4 volts, VGS 5 volts, VGS as 6 volts. To identify, locate the pinch off points. So this is nothing but locus of pinch off. Where constant current will result. Similarly, you can extend this to the for drawing transient characteristics. You can see that I will take sleeve here in terms of 1 volt.